Good. Seeing no questions, then we can start. Okay, so this is from last time. We have a function, f of x is 3x to the 2/3 e to the negative x over 3, and we're told its derivative, so we don't have to figure it out. It tells us negative x to the negative 1/3 power times x minus 2 e to the negative x over 3. And it says, which of the following is true about the critical points x equals 0 and x equals 2 of f of x? And there's 4 options. Some saying local min, some saying local max. There's even an option at the end which says one of them is neither min nor max. So we've got 5 options, A, B, C, D, or E. Which is the right option? C? No. A?
C.
It's C. Okay, so how do we know? Well, we use the first derivative test. So first derivative test basically says the idea of the first derivative test is let's use information from the first derivative. Now, the information the first derivative provides, am I going uphill or am I going downhill? Increasing or decreasing? So what we do is we say, okay, we know the critical points. We draw our number line. We mark 0 and 2. And here, I'm thinking like, well, I got a product of a bunch of stuff. So I'm looking at the signs. There's a negative. This is either positive or negative, depending upon whether x is positive or negative. Then you have x minus 2, which might vary. But e to something is always positive. It's the optimistic function. It's always positive. It's always looking on the bright side of life. So you plug in, and you discover that we go from decreasing to increasing back to decreasing. So local min, local max. And that's the answer. All right. Any questions? Good. Well, that brings us to our thought for the day. So this is from John von Neumann, a very smart mathematician. And he said the following, and it was a half a joke, but I think there's some truth to it. In mathematics, you don't understand things. You just get used to them. And what's sort of the underlying truth there? A lot of times we have this sort of, I don't want to call it fantasy, but we're like, we're going to have these big epiphanies. A light bulb will turn on and just boom. So like understanding comes in these big flashes. Now, in your life, you will have some flashes of insight, but they're not going to happen all the time. They're not going to happen with everything. When they do happen, enjoy them, relish them. And all right, and when they don't happen, that's okay. Say, wait, what happens? Well, the thing is, the way you learn is a bit at a time. It's incremental. So it's not going to be one big explosion, but lots of small steps along the way. You won't even realize you're learning. But by doing the work, you just get used to how things go. And sooner or later, hopefully sooner, it becomes second nature. You've gotten used to it. You understand the flow of ideas. You understand what's going on. All right. Well, that's today's thought. So, last time, what did we talk about? Do you remember? What was the theme of last time? Did people come last time? Yes? Okay. It was the first derivative. That was our theme. We talked about the first derivative. First derivative was like, hey, it's increasing or it's decreasing. If first derivative is positive or negative. We can tell what's going on at critical points. So first derivative gives us information. But as a hobbit might say, we've had one derivative, yes, but what about second derivative? Okay, that's today. So our goal for today is to figure out, hey, what does second derivative tell us? So if we think back, we say, well, if I think about the first derivative, it tells me something about the function. It tells me how the function is increasing or decreasing. So in particular, it says, oh, I can tell you if the value of the function is going up or if the value of the function is going down. That's the first derivative. So we say, well, the second derivative, that's the derivative of the derivative. Okay, so that says that the second derivative is telling us whether the first derivative is increasing or decreasing. Well, what is the first derivative telling us? It tells us the slopes of our tangent lines. So, we have the following conventions. We say our derivative f double prime is positive, means that f prime is increasing. And this is an example of where f double prime is positive. So let's think about the slopes. So over here, what can you tell me about the slope? And you can just make it very simple.
It's negative.
It's negative, right? It's going downhill. What if I move a little bit over? It's not quite flat, but comparing the two, yeah, it's sort of like less negative, right? Then here, it's 0, and then it's getting positive and getting more positive. So as we moved along the curve, of course we lost the curve because I chose a very dark color, but as we moved along this curve, what happened is that those slopes got more positive. And we have a name for this. We call this concave up. Okay, so concave up, it's something about the shape of our curve. Our tangent lines, the slopes are going up in a positive direction. Now, if our second derivative is negative, well, that means the slopes are decreasing. We call it concave down. So again, just think about your slope. So initially, it's a positive, slightly less positive, 0, going slightly negative, going more negative. So as we move from left to right, our slopes are getting more negative. And we are going to call this concave down. All right. So we have our two types of concavity. In essence, the concavity is trying to tell us information about how the curve is bending. So, in addition to concavity, we will have the notion of what's called an inflection point. So an inflection point is where concavity changes. So it goes from concave up to concave down. So it looks something like I'm concave up, I'm at an inflection point, I'm concave down. So this is the inflection point. So it's a change in concavity. Well, where can an inflection point happen? And the answer is, it can only happen where the second derivative can change sign. Okay, where can the second derivative change sign? Well, that's where the second derivative is either 0 or undefined. Now, this might feel familiar. It sounds an awful lot like critical points, because it basically is like a critical point. It's critical points for the first derivative. Now, be careful. When we talk about inflection points, we want to make sure it's where concavity changes. So it doesn't mean that if your second derivative is 0, you are at an inflection point. It means if your second derivative is 0, you could be at an inflection point. You have to check what's happening on either side. What's happening before, what's happening after. And you compare the concavity on both sides. That will tell you if your concavity changes. Now, I do want to make a comment about the names. Concave up versus concave down. And I think that there's something very nice and geometrical which can help. So, I've drawn here a picture. There's an unknown curve, and we don't know it, but we have the tangent line at a particular point. Now, that's not the curve, but the tangent line is a good approximation to the curve. The question is, what is the curve doing? How does the curve relate to the tangent line? Nearby, of course, it looks like the tangent line, but what if we step just a little bit back? Right? Because if we zoom in really close, we look like that line. So a little bit back, so we're not quite down to a line. So there's a little bit of a bend. What does a concavity tell us? So here's the moral. You can think of it as there's two sides to your tangent line. There's an upside, and what's the upside? The side that's up. And then there's a downside. Spoiler alert, it's the side that's down. If your curve is bending to the upside, this is when your curve is concave up. So if you have this, you are concave up. So concavity can tell you which side of the tangent line you're falling on. If, on the other hand, your curve is bending in the other direction, down here, this is when you're concave down. So concave up says you are bending up from your tangent line. Concave down says you are bending down from your tangent line. Okay, so that's probably one of the reasons we use the phrases concave up versus concave down. All right, any questions? Let's do some practice. So, find all inflection points for the curve y equals 9x e to the minus x squared over 6. Also determine where the curve is concave up and where it is concave down. Okay, so I have a curve. I see a word. I see lots of words. But I see words like inflection points and concave up and concave down. Those words tell me what? Now we need second derivative. So when you see inflection or concavity, that tells you, oh, this is information from the second derivative. So we know going in, this is a second derivative type question. Aha, oh, ho, 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 ho. So, probably we should start by finding the second derivative. It seems like a reasonable thing to do. So, we practice. What rule do we need to take the first derivative? Product rule. Do we want to walk through it slowly, or do you trust me enough to let me walk through it quickly? Quickly? Okay. The derivative of the first, 9, times the second, e to the minus x squared over 6. Plus the first, 9x, times the derivative of the second. Well, e to anything, you write down that e to the thing, times the derivative of the inside. That's the chain rule. And that would be minus 2 over 6x. Well, minus 2 over 6 is the same as minus 1 over 3. So this becomes 9 minus 3x. We'll go ahead and put those together. E to the minus x squared over 6. Okay, so that's first derivative. Any questions? In that case, we go to second derivative. Y double prime. Derivative of the first. negative 3 times e to the negative x squared over 6. So the derivative of the first times the second plus the first, 9 minus 3x, e to the minus x squared over 6. Oh, whoops. Ah! I forgot something. X and x means x squared. Ha! I knew this was looking too easy. Okay. All right. Derivative of the first would be negative 6x, e to the negative x squared over 6, plus the first 9 minus 3x squared times the derivative of the second, e to the negative x squared over 6 times negative 2 over 6x. So that makes negative 6x, e to the minus x squared over 6. That's a minus 1/3 x. So minus 1/3 x times 9 minus 3x squared makes a minus 3x plus x cubed, e to the minus x squared over 6. So we end up with x cubed minus 6x minus 3x times e to the minus x squared over 6. Okay, there we go. Now we're making progress. Okay. How did I do? I know I already made one mistake. So I always worry because mistakes tend to come in groups. It's like, well, I made one mistake. Did I make another? Does that look all right? Okay. All right. Well. Oh, I should have said minus 6x minus 3x. There's an easier way to write that. That's minus 9x. And I can factor an x out. So it's x times x squared minus 9, e to the minus x squared over 6. And x squared minus 9 is x, x minus 3, x plus 3. Okay, good. Now, what are we looking for? So if we're at a possible inflection point, what type of points are we looking for the second derivative? Second derivative can be either undefined. Is that ever undefined? No. Or it could be 0. Okay, so let's check. Is this e function ever 0? No, it's the positive function. Great. Can x plus 3 be 0? Yeah, at negative 3. Can x minus 3 be 0? Yeah, at x equals 3. How about x? Oh yeah, you betcha. At x equals 0. Okay, so there's 3 possible interesting places. So we'll mark them. Negative 3, 0, positive 3. And you might say, whoa, that feels like what we did last time. Draw a line, mark the points. Because it's the same ideas. Wow, it's great how that works. Okay, so what are we going to do? Now we do our test. We test each interval. So, do you have a number bigger than 3 that you like? 4 is a nice number bigger than 3, and you plug in 4 times 4 minus 3 times 4 plus 3 times this, whatever it turns out to be. Well, positive, 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 positive. So what's the conclusion about our second derivative? It's positive. Remember, we only care about the sign. So, 0 to 3, what's a good number? 1. Positive, negative, positive, positive. All together? Negative. How about from negative 3 to 0? Negative 1. Negative, negative, positive, positive. All together? Positive. All right. and negative 4. Negative, 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 positive. Altogether, negative. All right. So we say, aha. We see places where our second derivative is negative, and we see places where our second derivative is positive. Cool. So, the first question, inflection points. Do we have any inflection points? Yes. How many inflection points do we have? We have 3. They're all inflection points. They all correspond to places where concavity changes. So our inflection points are x equals negative 3, x equals 0, x equals positive 3. All right. Well, we were also asked concave up and concave down. Where are we concave up? Negative 3 to 0. We can use our interval notation, negative 3, 0. And whether you put a square bracket or parentheses, we'll still like you. Either way. We know what you mean. And 3 to infinity. Oh, by the way, whenever you have infinity, it has to be a round bracket. If you put a square bracket on an infinity, we will have discussions. We'll call you into the principal's office. No, we won't call you into the principal's office. Okay, concave down. Where is that happening?
Negative infinity, negative 3.
Negative infinity, negative 3, and 0, 3. Okay. All right, good. Any questions? Yes? Aha! For the same reason as last time. So concavity is about increasing or decreasing. But now, if you think about it, the first derivative is increasing, decreasing function. Concavity is increasing, decreasing first derivative. And increasing, decreasing, this is a philosophical discussion. But when we talk about increasing, decreasing, we're really talking about comparisons. You know, how does this point compare to that point in terms of the derivative? And so when we talk about comparisons, it's properties of intervals. So that's why we include the endpoints, because we can make comparisons with endpoints. There are other people who think differently, but that's okay. We get along enough.
Wait, how come e to the negative x squared over 6 isn't an inflection point?
Well, e to the negative x squared over 6, the question is, can this ever be 0? And the answer is no. The exponential function is always positive. So if you graph, I don't know why I'm having a, if you graph the exponential function, it looks like this, y equals e to the t. So as t gets big, it heads off to plus infinity. As t gets small, it heads off to a small number, gets close to 0. But it always stays above the line. It never goes negative. It never hits 0. So as soon as you have e to something, it's like, I know for sure, whatever it isn't 0. And so, in fact, if I see e to something, it's positive. Unless I'm in a course which has numbers which get a little bit more complex. And then interesting things can happen. But it's still not 0. Even in that case, it's never 0. Yes?
Are we going to have to take a third derivative?
Well, unfortunately, we're running out of lectures, so we're not going to talk about the third derivative.
Okay.
Now, one theoretically could. Now, the good news is, if you like lots of derivatives, have I got good news for you? You're just a few months away. Calc 2. The whole last third of the course is like, first derivative, that's beginners. Second derivative, nothing. I'm going to take all the derivatives. And when we say all the derivatives, we mean all the derivatives. Infinitely many. Don't stop. Don't stop. Just keep going. So, good news. It's a blast. Everybody who goes through Calc 2, they remember that class for the rest of their lives. So, I'm sure it's because of positive things. So, all right. Find the inflection points for y equals 2x to the 6th minus 6x to the 5th minus 15x to the 4th plus 29x minus 37. Also determine where the curve is concave up and where it is concave down. How many inflection points are there? How many are there? I hear some people saying 3, and I hear other people saying 2. Maybe we'll split the difference and say there are 2.5? No. The answer is 2. Why? Well, okay, we take the second derivative. Good news is it's really easy to take derivatives of polynomials. After you take the second derivative, factor it out. And there are 3 places, right? 0, -1, and +3. But the thing is, notice how it's x squared. So what's going to happen is you're not going to change sign. So it's the same type of concavity on both sides of 0. So it's not an inflection point. Inflection points are changes in concavity. Because you don't change, it's not an inflection point. So your inflection points are -1, +3. We're concave up, below -1, after 3, and then we're concave down in the middle. We can actually merge these together. Okay. Good. Well, now, what can we do with the second derivative? We talked about concavity. We can also do what's called the second derivative test. So, what was the first derivative test? The first derivative test was to say, suppose I have a critical point. What kind of critical point is it? Second derivative test is the same thing. Suppose I have a critical point. What kind of critical point is it? Now, there's some notes here. Both tests can help, but the first derivative test is more powerful in the sense it works more often. And it's usually easier to apply the first derivative test. And you might say, well, that pretty much rules out that I'm ever going to use the second derivative test. However, there is a reason you want to know it. And that's this comment here. It's a test that works in higher dimensions. So a year from now, when you're taking multivariable calculus, maybe not even a year, maybe you're going to go and speed run calculus. But you're going to get to a point where it says, okay, how do you classify? And you're going to find out first derivative test doesn't work, but second does. Now, if you think back to the picture we had, if we're at a place where our first derivative is 0, that says our tangent line looks like that. It's flat. And then we had the two sides. So we had the top side and we had the bottom side. So, you remember what side is what? If I'm on the top side, what type of concavity is that? Concave up. So here, this is your concave up, and that's going to be if your second derivative is positive. If you're on the bottom side, what are you? Concave down. And that's if your second derivative is negative. So that's basically the essence of the second derivative test. It says, hey, let's look at the second derivative. How am I bending off that tangent line? Am I bending up? If I am, I'm at a min. Am I bending down? If I am, I'm at a max. So, if the second derivative is negative, we went down, we're a max. Second derivative is positive, we went up, we're a min. If the second derivative is 0, more work. Doesn't work. The test is inconclusive. Now, the way I remember this is I say, if the second derivative is negative, I look like that type of curve. Right? Second derivative, I see two minuses. If the second derivative is positive, I look like this type of curve. And if the second derivative is 0, I have no idea. It's like that famous painting, The Scream. Ah! We just don't know. We just don't know. All right. Well, any questions about the second derivative test? It comes down to saying, what's the sign? Okay, so try it out. Here's a problem. Find the critical points for y equals x cubed minus 3x squared minus 9x plus 10, and use the second derivative test to classify. So determine if there are a max or a min using the second derivative test. How many critical points did we get? 2. Where are they at? -1 and 3. What kind of critical point is -1? Max. Good. And what kind of critical point is 3? Min. Okay, so to find the critical points are first derivative. Set the first derivative to 0. Solve. Second derivative is pretty straightforward. Don't use the factored form. Use the nice unfactored form. And you plug in, and you get negative and positive, and good. Last idea for today is curve sketching. Now, if you were a computer and you wanted to sketch a curve, what would you do? When you say plug it in, but you're the computer, and someone says, hey, computer, sketch this curve, what does a computer do? Point by point. A computer just says, hey, I'm going to plug in a whole bunch of points, and I got a bunch of dots, and we look and say, oh, that's a great job. We sort of, visually, we fill in between the dots. Now, suppose we do it. We are not as patient as computers. See, computers love to compute. It's in their name. It's in their nature. But we are not that patient. We don't want to put a billion dots. We want to say, well, where are the important dots? So we can use calculus to do efficient and pretty good curve sketching by playing industrial strength connect the dots. Industrial strength not in that we're going to have many dots, but rather we're going to have few dots, but have a good idea of behavior. So what do? Well, you start by finding all the points where the derivative and the second derivative are 0 or undefined. So we have this curve, y equals x cubed minus 3x squared minus 9x plus 10. That might feel familiar, as though you've seen it before. And, well, we know where the derivative is 0, and we know where the second derivative is 0. So there's 3 points. So that tells us there's 3 important dots. Now, once you have those, you actually plot them. So, for instance, you could plug in 1, and if we plugged in 1, you'd get a number, I think you get -1. If you plugged in 3, you'd get another number. I probably should have planned ahead, shouldn't I? And figured out what the number is. It'll be down here. And if you plug in -1, it'll be a number up here. Something like that. So you put in those dots. And I claim those dots, those are like really good dots. They're like the best dots for this problem. Now, where the derivative is 0 on those dots, you can say, oh, I secretly have a flat tangent line. So that's good to know. Now, the next step is you want to say how is the derivative and the second derivative behaving in those intervals? What are the signs? Because if I know the sign of the first and second derivative, I have an idea of how the curve is bending. So if the first derivative is positive, and say the second derivative is positive, I'm bending up. Or the first derivative could be negative, the second derivative could be negative. I'm bending down in a particular way, and so forth and so on. So there's 4 categories. So for us, if we go through, and in the interest of time, I'll say the first derivative is positive, and the second derivative is positive above 3. Between 1 and 3, the first derivative is now negative, but the second derivative is positive. Between 1 and negative 1, this is a place where they are both negative. And then below negative 1, we see that it's a place where the derivative is positive, but the second derivative is negative. So I'm doing this fairly quickly so we can finish on time. So now we say, great. We know what the behaviors are. So I see first derivative positive, second derivative negative. First derivative positive, second derivative is negative. That would be here. So I have to look like that. In the next interval, first derivative is negative, second derivative is negative. Okay, negative, negative says we have to look something like that. Then we have our inflection point. Then we have first derivative negative, second derivative positive, and that would be here. So we're going to start bending back to 0, and then finally we come up like this. So we can use just a very few points, but because we know the behavior, we can get a very good shape of the curve. So that's using calculus to sketch curves. All right, that's it for today.